Sometimes the axial members that we're trying to analyze can't be analyzed based off statics alone. So we call these indeterminate members, and you've likely been introduced to them in the past with statics, but a bit of a refresher is that we have a column here that's supported between two fixed supports at A and at B, the top and at the bottom, and has a point load applied at the intermediate location that's pulling down. And so I know just from basic human experience that the bottom is going to be in compression and the top portion is going to be in tension. But if I wanted to try to figure out what the reactions were at the top or at the bottom, or if I wanted to figure out the internal forces anywhere, statics alone isn't going to be enough to arrive at that answer. And we'll go through the steps. We'll do in a free body diagram of statics. It'll show us that we don't have enough equations to solve for the reactions or the internal forces here. And so mechanics of materials gives us the power to combine with statics another equation that also relates the forces in these members, not just based off equilibrium alone, but something that we call compatibility. And so in this example here, we have a prismatic column, and we have a length to a point load at the top, which you call LAC, and this is similar to the example that's done in your book in chapter 4.4. I'll do it slightly differently, but you can look at it for some additional description. The bottom we have member BC. And so it's not necessarily at half height here, it's some variable distance, but we know that both of them together add up to this total length, which I'll just call L. It's prismatic, and so the area of member BC equals the area of member AC. We don't have any discrete values for these. We're leaving everything as a constant, as just an unknown variable, I'm sorry. And the modulus of elasticity is going to be the same as well too. We're going to assume that these are equal and that these are equal. Just to, the only thing that we're varying is just the distance. And you can imagine, or maybe you would hypothesize, that if point P was exactly in the middle of this assembly, you might guess, and it would be correct, that if everything else was the same, the area, the modulus of elasticity, if this length was the same as well too, then half of this load would go down to the bottom support and half the load would travel up to the top support. It would be shared equally. And that's because we would have an equally stiff load path to go from here to the bottom as we have going from here to the top. And it's all about load paths. That's what delineates how much load gets carried in that direction. But like I said in this example, the length of member BC is different than the length of member AC. And we're going to figure out how to calculate the internal normal forces in the top section, the bottom section, and we'll see that these come into play in how much gets distributed to either. So your book doesn't call it the stiffness displacement method, but that's the name of this first method that we're going to use to try to solve indeterminate axial problems. Chapter 4.5 is called the force or flexibility method, and that's the other method which we'll go through in a different video. So for the stiffness displacement method, the kind of unnamed version in chapter 4.4 of your book, it's a two-step process, and those two steps, the first one is very familiar to us. And so just to write down what we're trying to find here, let's try to calculate the internal normal force in member AC and the internal normal force in member BC. Let's try to calculate those for this example. So the first step is to use statics and to apply equilibrium to try to calculate the desired values. So here the first step is equilibrium. And I'll just put in parentheses that we're just talking about statics here. So for the equilibrium step, we make section cuts in this case to try to find the internal normal forces, and then we use equilibrium to write an equation that tries to calculate those values. So there's no problem here with, I'm just going to make two different section cuts, one through the top and one through the bottom, to eliminate the support reactions, and I'm just going to consider the internal normal forces here. It shouldn't cause any problems, it's just a little bit of a shortcut. So I'll make 2 section cuts here, and I will draw a free body diagram showing both of those section cuts. It's kind of the same thing as trying to calculate the support reactions, but here I'm focusing on the internal normal forces. It's not a big distinction. I'm just focusing on internal normal forces, not the support reactions. So my free body diagram in that case, showing those section cuts, will have the column. I'm going to keep everything in between the section cuts. I have a section cut on the top, got a section cut on the bottom. And before I start drawing anything else on here, I'm just going to draw my internal normal forces. So here, I'm going to follow the sign convention for a positive internal normal force, just like we always do when we make a section cut. And so I draw it pointed away from the section cut from the remainder of the element that remains. So here, that will be pointed upwards. This will be the internal normal force in member AC. And at the bottom section cut, it'll be pointed away from the section cut, or in other words, down. That's the internal normal force in member BC. I need to draw the externally applied load as well, so we have point P, the point load P being applied at the location C. And geometry here is not important. None of these are distributed loads, so the geometry is not going to come into play. But I will put a coordinate system on here just because it's a good practice. So as you can see, these internal normal forces are essentially the reaction forces that we would have up here, but I'm trying to focus on the internal resultants, not the support reactions, which are just externally applied forces. Again, when we're talking about displacement in this class, we're always talking about internal forces, so it's usually the easier thing to focus on. So using equilibrium in step number 1, I'm trying to find NBC and NAC, and the only way to do that is by summing the forces vertically in the y direction. So if I sum the forces in the y direction equal to 0, my coordinate system says that forces pointed up are plus, forces pointed down are minus. And so we'll just go from the top down. I get NAC is pointed up, so that's positive. P is pointed down, so that's negative. NBC is pointed down, so that's negative as well. So I can rearrange this any way that I want. It doesn't really make a difference, but I will just say that NAC equals P plus NBC. Just a little bit of algebraic manipulation, but any format would be fine. But what we see here is that we can't solve for either NAC or NBC. It's indeterminate because I have one equation, but I have 2 unknowns. Again, we're assuming that the externally applied load would be a given value here. We're just leaving it in variable format. So I have one equation, and I'll call this equation 1, but I have 2 unknowns, so it's not enough. Statics won't allow us to solve this problem. So that's where mechanics of materials come in, and your book talks about needing another equation with these same 2 variables as the only unknowns in it. And so we can use what we know about displacement now to give us that additional equation, and that additional equation is called a compatibility equation. And compatibility, whereas equilibrium focuses on forces and moments and things like that, compatibility is concerned about displacements, and eventually we'll see rotations as well too when we talk about torque. And so here I need to know something about the relative displacements of member AC and member BC that I could then turn into an equation that has the normal forces in it. So then I have a second equation with the same 2 unknowns, 2 equations, 2 unknowns. I can solve those simultaneously, just like from linear algebra, and I can actually get the internal normal forces as a result. So just like with the equilibrium step, you need to draw a diagram that shows this relationship between the displacements of members AC and BC. But we don't make section cuts for a compatibility diagram. We just basically draw the original shape. And you don't even technically need to draw the displacements on there. So you don't need to draw the force on there. We can just start looking at the displacements. And so here, there's a couple different ways to get this step done correctly. One, the most important thing that we know here is that this overall length between the fixed supports, it can't change. This is a rigid support, this is a rigid support, so the overall length can't change. And that overall length is equal to the length of member AC plus the length of member BC. We know that delta L has to be equal to 0. The change in length equals 0, which by extension simply means that the change in length of member AC plus the change in length of member BC, also has to be equal to 0. Another way to put that is the point where that load is being applied, P is being applied at point C. So this point here is free to move down or up or anywhere that it wants. And that's going to change the length of member AC or the length of member BC, but the overall length won't change. So for example, here the point load is being applied in a downwards direction. So member BC, let's say it shortens an inch. That means that member AC has to get an inch longer. And so that's kind of what tells us how much force gets distributed to the bottom to the top, but the equation fundamentally just says the relationship between the deflection, the change in length of each of the members. And so this equation right here is kind of the start of our compatibility diagram or compatibility equation. In other words, it says that delta AC plus delta BC equals 0. But that's not exactly what we need. We need another equation that has the normal force in AC and the normal force in BC as the only two unknowns. But here, this is the change in length. These aren't forces. But I can use what we know about the deflection of an elastic member, elastic axial member, to turn those into equations that have NAC and NBC in it. And so each of these members, BC and AC, each only have their loads or reactions applied at the ends, and they have a constant cross-sectional area. So those are just individual little columns that we can define the change in length of as just NL over AE. So this is NL over AE for member AC plus NL over AE for member BC equals 0. Or in other words, let me reorganize this a little bit. I'll just say the left side is equal to minus the right side. And just to make this as clear as possible, I will distribute AC and BC, the normal force in member AC times the length of member AC divided by the area of member AC times the modulus of elasticity of member AC equals minus the normal force in member BC times the length of member BC divided by the area of member BC times the modulus of elasticity of member BC. So now, the only two unknowns that I have, NAC and NBC, are in both of these equations. We can assume the geometry, the material properties are all given to us as part of the problem statement. So it's really just NAC is over here and NAC is over here. NBC is over here, NBC is over here. And so this is at a proper stage to call it equation number 2. And so I have 2 equations, I have 2 unknowns, so I could solve for NAC or NBC as I choose. So here we can simplify things even more if we want to. So this is a very simple example where the only thing that is different between AC and BC is just the length. The areas are the same, the modulus of elasticity is the same. So in terms of relative stiffness, area and modulus don't make any difference whatsoever. And you can see that algebraically here. If EAC and EBC are equal to the same thing, they just cancel out. That cancels out with that. Likewise, the areas, area of AC and area of BC are exactly the same, so they cancel out as well too. And so this boils down to, you could put it a couple different ways. Let's just say that the normal force in member AC is equal to minus the normal force in BC times the ratio LBC divided by LAC. And so if that's the case, I can plug in this value right here, P plus NBC, into the left side of this equation, and all that I will have left are NBC as the only unknown value. And so if I do that, make some space over here, and I get P plus NBC equals minus NBC times LBC divided by LAC. And I could say P equals minus NBC times LBC divided by LAC minus NBC. So I can distribute this out if I'd like to, and I can say P equals minus NBC times 1 plus LBC over LAC. I could flip the signs and then I could solve for NBC, and I would say that NBC equals P divided by 1 plus LBC over LAC. And so that allows us to solve for the internal normal force in member BC. And so you can see, let's do a couple of experiments here. Let's talk about if the length in member BC was equal to the length in member AC, this ratio would be equal to 1. So I'd have P divided by 1 plus 1, or P divided by 2. In other words, that means that if these lengths were the same, half of the load would go into member BC and half would have to then go into member AC. So that makes sense. There is a way to simplify this a little bit more as well too. We can say that this ratio is also simply equal to, if you do a little bit of substitution here, we can also say that this is equal to P times the ratio of LAC divided by the total length L, and you would get the same result as well too. So if the length of member AC was equal to half the length, it would be P times 1/2, same exact result. Likewise, if this point load was applied way down here, really close to point B, then my length AC would be really big. It would be really close to L. So if that was the case, I'd have P times something close to L divided by L. It would be P times something close to 1. because if I apply the point load way down here, most of it's going to go into that bottom member, down to this support right here. So once we have that equation figured out, once I've figured out NBC, I could then plug this back into, let's say, this equation right here, and I could solve for the force in member AC. What we end up getting if we do that is we get the normal force in member AC simply equals P times the length of member BC divided by the overall length of the assembly. So this is member BC down here. This is member AC up there. And you can see it's a very simple relationship, and it's only based off the lengths of the members. And that makes sense because they're both materially as stiff as each other, and they both have the same geometric stiffness in terms of cross-sectional area. So the only thing that can make the difference is the length of each section. So this method again is called the stiffness displacement method. Step number one, we use statics to try to find either our reactions or our internal normal forces. We won't have enough information to solve for both of them or for all of them. There could be more than two because it's indeterminate. If you get to this point right here and you can actually calculate the normal force in AC and BC, then it's not statically determinate. You don't have to worry about any more steps. Be careful about that though. Make sure you're doing your statics right. Especially if you're in the statically indeterminate problem set, you want to make sure that you don't interpret this as a determinate problem. So that's going to get us one equation with two unknowns. And we need another set of equations to solve for, for actually both the unknowns. And that other equation comes from compatibility. And there's different ways you can draw your compatibility diagram, but just make sure to always draw a diagram, and it's going to be some relationship between the displacements of each of the members. And then you need to use mechanics of materials to get that into a form that has the forces in each of the members as part of the equation. And just like here, you're going to get down to two equations with two total unknowns. You can use linear algebra or substitution to then calculate what each of the unknown values are going to be.